So welcome to the last panel of the morning. It's a panel on AR and neuroscience, and I didn't coordinate at all with the previous speakers, but they gave us a great intro. And if if the crowd thought about, is it AR and neuroscience something legit? It is legit because you've heard from the previous speakers that machine vision people think that human vision plays a little bit of a role, and along with vision, a brain. In fact, there is two starting reasons why we should consider like neuroscience and humans in this loop. One is that we are literally like showing a computer to our senses, to our eyes. We can no longer discard them if you don't want to. The second is that these displays, they don't serve the space of our ideas. Sometimes, we keep jotting down stuff here, but we have lots of post-its around because we want our ideas to float in space, okay? And this is what we're getting with these AR technologies, okay? So my name is Stefano Baldassi. I'm the director of analytics and neuroscience at Meta company. And I joined Meta almost 3 years ago. But before then, I had 15 years of tenured academic life in visual neuroscience. And I decided to give up my tenureship because the challenges in research, in understanding this deep connection between technology and the human cognitive system, if you want, has a number of research challenges that are as challenging as the pure basic academic research for me, okay? And I will be moderating this panel, and in this panel we have three women speakers, fantastic, who are neuroscientists, and they will introduce themselves now.
Hello, I'm Mo Qian. So I got my PhD in psychology, specializing in neuroscience from Stanford in 2016. I studied how people recognize faces and objects. After that, I joined Meta as a researcher, using my neuroscience training to answer questions and research in ergonomics, design, hardware, sensor calibration, machine learning projects.
Hi, my name's Jacqueline Snow. I'm an assistant professor in cognitive psychology and neuroscience in the Department of Psychology and the neuroscience program at the University of Nevada in Reno.
And I'm Caroline Robertson. I'm a neuroscientist based here at MIT and at Harvard. And my research specializes on using neuroimaging techniques in order to understand the neural basis of visual cognition.
So I would start with Mo Qian. You have a vantage point on both basic neuroscience and AR. Can you expand on the connections between?
Yeah, I think it's a very interesting connection between neuroscience and AR because it doesn't occur naturally to everyone, what the connection is. Actually, when I joined Meta as a neuroscientist, I got questions like, so is this just a PR for the company? And because neuroscience is such a buzzword nowadays. But I obviously think that it's not just a PR. Actually, if you think about it, neuroscience is not just dissecting rats' brains in the lab. It involves studies from basic visual perception, audition, attention, memory, to social behaviors that use methodologies like psychophysics, eye tracking, EEG, modeling. So in our most high-level question in augmented reality is that in the first time, we live in this world where we have superimposed images on our real world. So how do our brains deal with this duality? I think it's not very exaggerated to say that it's key to understand how the brain works to build the most comfortable augmented reality. And this seems to be a grandiose question to ask, but there are already a lot of low-hanging fruits. For example, when you have to build a virtual scene, you have to put lighting source in the scene. So unless you have a built-in camera that detects the environmental light and apply that to the virtual scene, we might as well put in a constant lighting source in the virtual scene. Our brains have prior assumptions that lighting usually come from the above and a little bit to the left. Just by using that knowledge, we can build more naturalistic virtual environments. Another example is latency caused by rendering. So what is an accepted latency before we can perceive it? And what is that number before we start to feel annoyed? Is there a perceptual mask that we can use to trick the brain into ignoring the latency? Or is there an algorithm that we can apply to the rendering process that reduce the rendering load and reduce latency, but without hindering our perception and the perceived image quality? So there are countless questions that are waiting for neuroscientists to answer with real experiments.
Thank you. Yeah, and one of the things that I haven't highlighted in the introduction is that, yes, neuroscience is needed for AR, but AR and VR are also incredible tools for neuroscience. So I would like Caroline to tell us what do you think, what kind of research you've been doing, and how that can become like a tool for neuroscience.
Sure, definitely. I think that the advent of head-mounted VR and now moving into AR has definitely opened really exciting avenues for research for us, but they're all quite new. So I think there's sort of three new features for me, from my perspective, and then maybe Jacqueline can comment from her perspective, because we both research a different type, a different level of visual neuroscience. I focus on scene perception, especially panoramic scene perception, as opposed to object representation in the brain. So from my point of view, it's just been a game changer to have the ability both to have an experimental setting where we're not just looking at how a person represents a visual stimulus that they see on a flat screen, which fits into a single field of view. But now we can teach them full environments that are both within memory and also triggered by the scene that you have in a single field of view. So we've been using this in our lab in combination with fMRI in order to learn which regions of the brain represent full panoramic expanses and knit together moment-to-moment views that you have of an environment into a full 360 representation. And that was something we were just unable to do when our subjects were being taught environments simply on computer displays. And certainly having the command over a more egocentric visual perspective instead of an allocentrically taught image is a big deal for us as well. And obviously being able to have visual images which are given to the user through self-directed motion, self-motion in the environment instead of passive viewing, opens up new avenues of questioning for us as to how that motion in the environment is changing the way that we take in visual information. We've known for a long time from animal research that that is a huge deal, that animals that are raised in environments where they can't move through their visual scene have fundamentally different, fundamentally weaker visual responses as they grow into adults than those which are allowed to walk through a hallway or walk through a carousel. But we have not been able to answer on the human level until now why that is. What is it that self-motion is offering the brain in terms of building a visual representation?
This is very cool. So on the flip side, there is basic deep research in neuroscience that can inform the AR product at a deep level and influence in a positive way even the future generation of AR products. And I would like, and Jackie can give us a little bit of hint of her research and now that can inform the product.
Thanks, Stefano. So you're right. Most of what we know, neuroscience has a lot to contribute to the development of VR and AR. So it is a fact that most of what we know at the moment in terms of human neuroscience is the study of two-dimensional images. That's what human neuroscience has been focused on for a number of different reasons, which I'll outline in a talk tomorrow. But as a result of that, really the assumption is that two-dimensional images are equivalent to or suitable proxies for real-world tangible objects. And so one of the questions that we've been looking at in my laboratory is whether that is actually the case. So we've actually been testing both in the laboratory and in the MRI scanner and doing some work with neuropsychological patients with discrete brain damage and looking at whether the way we behave towards and the way the brain responds to real-world objects is the same as or different to two-dimensional images. And we've been also looking at some stereo images as well. And the big picture is that they're actually quite different. So we've found that there are a number of distinct signatures of realness that you don't see with two-dimensional images, both behaviorally and specifically in brain-based responses. So for example, as measured by functional magnetic resonance imaging or fMRI. So basically there is the brain response is really quite different to real-world tangible objects. And so this raises the question of what AR can potentially contribute to our understanding of why that is the case. So we've heard a lot today about the what's and the where can we go with AR, but I think what we really need to focus on in order to make that advance is to think about why. Why are we seeing these differences? And how can we understand this based on human behavior and brain responses?
Thank you. So, Moshan, after this first round of discussion, is it more neuroscience for AR or AR for neuroscience?
I think we're hearing a little bit both from these two other panelists. And I think it's actually both because I tend to think that every time we adopt a new technology, there are a lot of neuroscience studies being inspired. For example, the accidents caused by texting and driving inspired a lot of neuroscience on divided attention. And the emergence of the gaming industry inspired a lot of publications on addiction. So these are bad examples of how the technology inspire neuroscience. But I think AR could be a good one. Because like if we can imagine that we can study how our brain build a continuous experience based on, we know that the inputs from our eyes to our brain is actually very discontinuous in both space and time because of our saccadic eye movement. So imagine millions of hours of eye tracking data from the headset can contribute to this kind of questions. And I think both Carolyn and Jackie's study are good examples of this approach. But before we provide you guys, who are academic researchers, a tool, we want to provide you a very intuitive interface and to make this technology very usable. So together with Stefano and Meron, we drafted this document called Spatial Interface Design Guidelines, Augmented Reality and Neuroscience. In this guideline, the first thing we want to convey is that in a traditional UI, you only get 2D images, which activates our ventral pathway that process shape and form. But in augmented reality, it's the first time that we engage a lot of our dorsal pathway in the visual cortex, which process motion and space. And we're going to do a lot of empirical studies to test those hypotheses and what's the best way to utilize this more information. And I think that's a good start to connect this neuroscience and AR.
Thank you. So in these very early days these are the early days for these technologies, right? Some speaker in a panel before were referring to these as being like computers in the late 70s, early 80s. We have to admit we're in a similar stage right now for this technology. And one of the big questions that neuroscience can help solve, I will say something in my talk this afternoon, but one of the big questions is how we make that technology, both the hardware and the software, scalable to the masses, given one big problem even in neuroscience, in basic neuroscience, which is individual differences, right? So how can neuroscience contribute to scaling AR product to the masses, which is everybody will wear that seamlessly? Jackie.
To me, okay. So by scalable, I take that to mean, I think that some of the goals for AR should be to make it easier to wear, certainly easy to use and less invasive to wear, and to make the images or representations that we're looking at be as realistic as possible. And at that point, the user interface is more likely to become embodied in the sense that we sort of treat it as an extension of ourselves rather than, a device that we're pulling out. And we've heard this time and time again throughout some of the talks this morning. So I think at that point, and only when we've reached that point, is it going to become a more useful tool to then enable us to actually augment and, develop in the sense that we can use it to enhance memory and attention, and the way we attend to information in the world and how we perhaps make decisions about objects in our environments. So I think, the richer we make a visual stimulus, the more we're able to understand, we get a richer picture then about human brain function. And when we start to get a richer picture about human brain function and what AR is telling us, from the information that AR is telling us, then that in turn increases the usefulness of AR and makes it more useful to a number of different applications. So for example, we could see once it becomes less invasive to use, it might be more useful, for example, to treat patients with brain damage, for example, to either restore function or help them to compensate for lost function, or for use in learning settings, for example, to help students attend to information and therefore remember it more and facilitate learning.
Thank you. Caroline, what would be the ideal AR product for a neuroscience lab?
That's a big question. Maybe I'll take that to mean what features of AR would we be looking for as experimentalists? And I think many of them are there in terms of being able to control the presentation and timing of stimuli. But additionally, especially as neuroscientists, we'd like to have readouts from the person as well to know how they're processing the information implicitly and online. So the combination with eye tracking is very important for us in that regard. And perhaps not simply eye tracking, but also the ability to read out, say, pupil diameter, which are nice implicit measures of how much a person is attending to a part of space or an object, and also microsaccades, which are very, very small movements of the eyes, which give you a sense of where a person is about to look before they've even made that eye gaze. And these types of readouts from the person, I think, are important for us for making inferences about how we're processing the visual information. It's a shame this technology will probably never be compatible with the neuroimaging techniques I use. It will never have AR in an fMRI machine. That's a technical limitation, I imagine. Yeah. But the thought of combining it with EEG is a reality, and we can gain certain insights from that.
Yeah, this is interesting. The integration with EEGs is, I get this as a constant question. As what do you do? I'm like director of neuroscience. You guys have an EEG, or because there's this BCI industry, brain-computer interface industry, that's creating this demo in tech conferences in which you move a little like cube up and down based on some, signature like from electrodes that have a lot of noisy channels though. So the thing is, do you guys believe in EEG at the state of the art? These days, EEG and BCI in this technology. What is your quick response?
I think to some degree, I haven't necessarily seen experimental demonstrations of the compatibility of AR and EEG, but in theory, the ability to frequency tag different stimuli in a visual field with AR, that would allow you to read out implicitly where a person is attending without just using their eye gaze. So I could be looking here, but if I'm paying attention to an object that's flickering at a certain frequency here, you can read out that signal in the brain in a very robust way. That is the level of EEG that I think could be informative at this point.
Yeah.
So I think just to add to what you said, and to put this in context, so with EEG, we're able to get really nice we have really good temporal resolution. We can tell the timing at which different brain areas come online. as opposed to something like fMRI, where we get very high spatial resolution, so we can see which brain areas are activated. So although we may not be at the point yet where we can bring something like AR into the MRI scanner, we can use EEG to look at what parts of the brain might be active sooner or later than others and which brain areas are actually activated. So coming back to the point that Mokian brought up earlier, it's really exciting to think about the fact that if using AR we can get more realistic representations of the real world, and this might be more likely to activate dorsal brain areas that are involved in action and somatosensation, and then we can start to look at perhaps the timing of which these dorsal stream brain areas are activated relative to ventral, more perceptually based areas.
So I think we should go to the handing of this. So I'm very, very proud. I think this has been the first AR and neuroscience panel ever. John, what do you think? And
another one later today, but this is the first time.
that's the first time. And it's the beginning of a conversation that you know, we went through a few aspects, but there are so many aspects. And the conversation is starting. This is the first panel of a kind in a tech conference. But there's going to be a similar panel at the Vision Science Society meeting in Florida in May, organized by scientists for AR and VR, by vision neuroscientists. And this is going to be the first from the other side. But those two sides are going to merge very soon, because the conversation needs to get like one. And I think, this is a personal guess, there will be a field of neuroscience that will deal with how humans, whenever we get to the masses, will interact with this type of information that will become pervasive in our reality, in our world. So we will have to understand how the brain react to that, and there will be maybe even some psychiatry of AR and VR in the future. Okay.
Let me just jump in for a second. I love Stefano, and he said to me, the eye can take in 10 to the 8 bits per
10 to the 8 bits per second is an estimate on some rodents.
So when you think of Ben Franklin and how movable type was laid out, that's why the QWERTY keyboard, because the things were so small, and so people would memorize where the letters were. And when they made the typewriter, they made it even less efficient so the keys wouldn't get jammed. So we type on our digital devices based on, you know, something else. And these guys are saying, why not base how we interface with technology based on how we run things? And as we think of AR, it's going to be spatial. And these two-dimensional screens that we've developed with Windows and iOS and Android and so on, they're not doing it, and there's a real opportunity to kind of do something big. And I think people like these are going to be like the heroes who are going to help us be more productive, learn better, and really navigate. And so if you haven't tapped them, you know, get to know these people, and I'm really glad, like I said, we're making history. You guys are the first that I know of like this, so thank you.
Thank you.